Final example, we have a very complicated function. F of t is 3 cosine 4t minus 2 sine 5t plus e to the 2t plus 3t squared plus 7t minus 2. And we want to find the Laplace transform for that. Now, if we use the definition of Laplace transform, by definition, we'd have to do the integral from 0 to infinity of e to the negative st times f of t dt. And our f of t would be this enormous expression, so we'd have to plug all of that into f of t, and we just get this horrific integral, and we really don't want to do that. So there's a much better way. We're going to use linearity, and we're going to exploit the fact that we already know what the Laplace transforms of the various pieces of this function are. So this linearity of the Laplace transform is going to be extremely useful here. We already know what the various pieces of the function do when you take their Laplace transform. So L of 1, we figured this out. This was back in example 1, so you might want to go back and check at example 1 if you don't remember this. It was 1 over s. L of t was 1 over s squared. L of t squared was 2 over s cubed. I'm kind of looking at the various pieces of this function here, and I'm trying to remember what the Laplace transform of each one was. So this came from example 1. If it's been a while since you worked through example 1, maybe go back and take a peek at that, and you'll see where these come from. L of e to the at is 1 over s minus a. So that, I believe, was example 2. So you might want to go back and check that out if that doesn't look familiar. L of cosine of at, worked that one out in example 3. And that was s over a squared plus s squared. And finally, L of sine of at was a over a squared plus s squared. And we worked that one out in example 4. So we're not really going to do any new math in this example. We're just going to exploit all the work we did in all the previous examples, and it should be pretty quick. So I'm going to read through, I'm going to look at this f of t. So that's, I see, first of all, 3 cosine of 4t. So here's my Laplace transform for cosine of at. So that the Laplace transform of f is, from the 3 cosine of 4t, I'm going to get 3. Now cosine of 4t is going to give me s over 16 plus s squared, because the a is 4 there, minus 2 times the sine of 5t. Well, sine gives me a over a squared plus s squared. A is 5, so 5 over a squared plus s squared, 25 plus s squared, plus e to the 2t. Now, I can read that one right here. That's plus 1 over s minus 2, plus 3t squared, plus 3. Now, t squared gives me 2 over s cubed, so 3 times 2 over s cubed, plus 7t, plus 7 times 1 over s squared, minus 2 times 1 over s, because the Laplace transform of 1 is 1 over s. So maybe I can clean that up a little bit. That's 3s over s squared plus 16, minus 2 times 5 is 10 over s squared plus 25, plus 1 over s minus 2, plus 3 times 2 is 6 over s cubed, plus 7 over s squared, minus 2 over s. So that's my Laplace transform of this large, complicated function here. And let me recap how we worked that out. We didn't want to go back to the definition of Laplace transform. That would involve writing the integral of e to the negative st times f of t, where f of t is this enormous function. So it would have been a horrible integral to work out from scratch. Instead, we're going to use linearity, and we're just going to break this function up into its pieces. And each of these pieces is something that I figured out the Laplace transform of in an earlier example. So first I looked at this polynomial. We have the basic pieces there are 1 and t squared. And so we figured out the Laplace transform of each one of those in example 1. Laplace transform of 1 is 1 over s. T gives us 1 over s squared. And t squared gives us 2 over s cubed. So I got the Laplace transforms of each of those. E to the at, in example 2, I figured out its Laplace transform is 1 over s minus a. And then for the cosine and sine, I figured out the Laplace transforms of those in example 3 and 4. Those were s over a squared plus s squared and a over a squared plus s squared. So what I did was I took each of those functions and just plugged them back in here and then attached the right coefficients. So 3 over the transform of 4 plus of cosine of 4t. Cosine, well, my a here was 4, so that's where I got that 16 plus s squared. For sine, my a was 5, so that's where I got that 5 and that 25. Plugged in the negative 2 as a coefficient here. E to the 2t, my a was 2 there, so plug that in there as 2, and I get 1 over s minus 2. And then t squared gives us Laplace transform as 2 over s cubed, so there it is there. Laplace transform of t and the Laplace transform of 1. And then I just kind of cleaned everything up. Combined the 3s. 2 times 5 is 10. And combined 3 times 2 is 6. And combined everything together. And finally I got that Laplace transform of that big, horrible function without ever actually having to do any new integration. I just relied on what I had worked out in the previous examples. So that's the end of our lecture on Laplace transforms. In the next lecture, we're going to learn about inverse Laplace transforms, learn how to go backwards from sort of the answer of a Laplace transform back to the original function. So that's our next lecture in the differential equations series here on Educator.com. My name is Will Murray. Thanks for watching.